Hi, this is Dr. Habib Ahmed, and today I'm going to show you how to perform the Silvaco TCAD simulation of metal semiconductor metal photodetectors. Before running the simulation, let me give you a brief introduction into this topic. An MSM photodetector, also known as a metal semiconductor metal photodetector, is a type of photodetector used to detect light and convert it into an electrical signal. The metal semiconductor metal photodetector consists of two metal electrodes, as you can see over here, typically made up of materials like titanium, aluminum, silver, copper, or you can say gold. And these two metals are separated by a narrow gap. This gap is usually filled with a semiconductor material, for example, silicon, gallium arsenide, or indium phosphide. When light is incident on the semiconducting material between the electrodes, it generates electron-hole pairs. And this process is also called photoexcitation. These charge carriers are then collected by the metal electrodes due to the potential difference applied across them. The incident photon create electron-hole pairs in the semiconductor, which causes a change in the conductivity of the material. This change in conductivity leads to a measurable current or voltage across the electrodes, which is proportional to the intensity of the incident light. Now, talking about the applications of metal semiconductor metal photodetectors, these kind of photodetectors are used in various applications where fast response times and high bandwidth are required, such as optical communications and fiber optics, optical interconnects, and high-speed photo detection systems. The MSM photodetectors are known for their simplicity of fabrication, high-speed operation, and low capacitance, which makes them suitable for high-frequency applications. Overall, metal semiconductor metal photodetectors play a crucial role in converting optical signals into electrical signals efficiently and are essential components in making modern optical communication and sensing systems more efficient. Now, I already discussed that in a metal semiconductor metal photodetector, we have two metal electrodes separated by a semiconductor. And basically, we form two Schottky junctions in this configuration, or you can say two rectifying barriers in this configuration. One rectifying barrier over here for this metal semiconductor, and another rectifying barrier for on the right side for this metal and semiconductor. And you can see these rectifying barriers in the energy band diagram over here as well. Looking at the Fermi energy level, you might see that the Fermi energy level in the semiconductor energy band diagram is close to the conduction band. Since it is close to the conduction energy level, we know that this is an N-type semiconductor. So in today's video we will talk about metal semiconductor metal photodetector based on N-type semiconductor. Let's talk about a few basics of the metal semiconductor junction, or we can say Schottky barrier, or in other words, a rectifying barrier. Now, one condition, before that, let me tell you what we are looking at. So basically, here is the energy band diagram of the metal on the left side. And here is the energy band diagram of the semiconductor on the right side. And we are looking at the energy band diagram before making contact. So, if you look at the metal work function, here is the metal work function, and compare it with the semiconductor work function, you might see that the metal work function is greater as compared to the semiconductor work function. And this is a precondition for making a Schottky barrier onto an N-type semiconductor. So remember that for creating a Schottky barrier to an N-type semiconductor, the metal work function should be greater than the semiconductor work function. For example, in today's simulation, we are going to perform Silvaco TCAD simulation onto an N-type semiconductor. Which is silicon, N-type silicon in our case. So the electron affinity of silicon is approximately 4.01 electron volts. And if we make it N-type, the Fermi energy level would be close to the conduction band. So our semiconductor work function would be somewhat closer to the electron affinity of the semiconductor. So if the electron affinity is 4.01, our semiconductor work function would be slightly greater than that. You can say, for example, 4.1 electron volts. Now, on the other side, on the metal side, if we assume our metal to be, for example, gold, the work function of gold is higher than 5 electron volts. Assume in this case it's 5.1. Now this metal work function is greater than the semiconductor work function, so this kind of configuration would result in a Schottky barrier. And for further details, you can look up my YouTube video posted on metal semiconductor junctions, in which I've given details about metal semiconductor junctions. I've talked about both rectifying barriers and non-rectifying barriers and tunneling barriers on N-type semiconductors and P-type semiconductors. So that lecture is really descriptive. So here is the energy band diagram before making contact. What happens when the metal and the semiconductor make contact? So notice over here that the Fermi energy level on the semiconductor side is higher as compared to the Fermi energy level on the metal side. So basically, when we connect them together, electrons would start moving from the semiconductor to the metal side. So as you can see over here, this is going to result in a depletion region across the semiconductor. And under thermal equilibrium, we would see a constant Fermi energy level. So now we have a Schottky barrier, and it's called phi b naught, and also we have got a built-in potential barrier. So basically, the Schottky barrier over here on the metal side is the potential barrier seen by electrons in the metal to move from the metal to the semiconductor side. Similarly, the built-in potential barrier on this side, on the semiconductor side, is the barrier seen by electrons to move from the semiconductor to the metal sides. And we have got formulas for both of them for calculating the Schottky barrier and for calculating the built-in potential barrier. Under forward bias, this barrier on the semiconductor side is going to be reduced, making it easier for electrons to flow from the semiconductor to the metal side. Under reverse bias, this built-in potential barrier on the semiconductor side further increases, making it difficult for carriers to move from the semiconductor to the metal side. However, if you focus on the three energy band diagrams under thermal equilibrium, under forward bias, and also under reverse bias, you might notice that the Schottky barrier remains the same under thermal equilibrium, under forward bias, and also under reverse bias. So now let us move back to our topic of metal semiconductor metal photodetector. In this case, we have got two Schottky barriers, one on the left side and one on the right side, as you can see in the energy band diagram as well. Now, under thermal equilibrium, we would have a certain depletion region. Under dark conditions, we would have a certain depletion region, a depletion width, making it difficult for carriers to move to the right and left electrodes. On under the application of light, when light is incident onto the semiconductor, it's going to result in the generation of electron-hole pairs. These electron-hole pairs would be attracted to these opposite electrodes based on the biasing across the external circuitry. When these carriers move to the junctions on the right and left side, it's going to result in a decrease of the potential in the depletion width. As you can see, under dark conditions we see a larger depletion width. Under light conditions we see a smaller depletion width. So due to this smaller depletion width, it's going to be easier for carriers to move across the junctions and result in a flow of current across the circuit. And I'm going to show you the comparison of dark versus light conditions for the metal semiconductor metal photodetector that we are going to simulate. So let's now turn to the simulation of metal semiconductor metal photodetector. I start with Atlas, and the first thing I do is I define meshing. My structure is running from 0 to 10 micrometers in the x direction. Here is this one is not the structure. So let me run the simulation a little bit so that we can see the structure. Okay, and I'm gonna kill it at this point. So here is the structure. Okay, an N-type silicon material, and we have got two electrodes deposited on top of that, the anode and the cathode. This purple region over here on the right in the middle, and over here on the left side, these regions actually represent air in the structure. So my structure is running from 0 to 10 micrometers in the x direction, as you can see over here, and from 0 to 1 micrometer in the y direction, from 0 to 1 micrometer in the y direction. This block over here represents the meshing, so I'm going to show you the meshing as well. I right click on the structure, click on display, and I click on meshing, then hit apply, click OK. So now you can see the meshing. I have defined denser meshing in regions of interest and also at the interfaces, and I've defined sparser meshing elsewhere in the structure. Then I have defined region number 1, which is silicon, running from 0 to 10 micrometers in the x direction and from 0.2 to 1 micrometer in the y direction. So this orange region over here represents the silicon region, running from 0 to 10 micrometers in the x direction and from 0.2 to 1 micrometers in the y direction. Then I have defined region number 2. The material is air, running from 0 to 10 micrometers in the x direction and from 0 to 0.2 micrometers in the y direction. So basically this purple region from 0 to 10 micrometers in the x direction and from 0 to 0.2 micrometers in the y direction represents air. Initially I have introduced it as air, and later I have introduced the anode and cathode regions inside this air region. Region number 3 is gold, running from 2 to 4.5 micrometers in the x direction. So as you can see, this is my region number 3, running from 2 to 4.5 micrometers in the x direction and from 0 to 0.2 micrometers in the y direction. And you can see the label over here as well. It's labeled as anode. Similarly, region number 4 is gold once again, running from 5.5 to 8 micrometers in the x direction. So this region over here, running from 5.5 to 8 micrometers in the x direction and from 0 to 0.2 micrometers in the y direction, is my cathode region. after that, I have assigned anode to region number 3 and cathode to region number 4. Then I create the structure, and then I start another module of Atlas, where I import the previously created structure named as MSM PD, where PD stands for photodetector. Then I introduced an N-type doping of 1 into 10 to the power of 17 per centimeter cube for region number 1, which is silicon. In order to see the dopings, I click on doping, I go to define, contours, and then I go to, I'm looking for net doping, hit apply and click OK. So as you can see that region number 1, which is silicon, is N-type doped with a doping level of 1 into 10 to the power of 17 per centimeter cube. Up here I have set the work function of the anode and cathode to 4.9 electron volts. So here is my anode, here is the cathode. I have set it to 4.9 electron volts. I have named it as gold, and generally the work function of gold would be higher than 5 electron volts. But here I've included the names and values for the sake of understanding. You can name it anything else like platinum or palladium or something else, where the work function matches with the name of the metals. Then I've assigned electron and holes recombination lifetimes for silicon, and more importantly, I have included the SOPRA file for silicon. If you are dealing with photodetectors, or if you are dealing with the solar cells, you need to include the optical properties of all the materials, especially the semiconducting regions that you are working on inside this structure. Here my semiconductor is silicon, so I have included silicon111.nk file, where N stands for refractive index and K stands for absorption coefficient. So basically the SOPRA files contain the optical properties information. More specifically, they contain the refractive index and absorption coefficient versus wavelength information for these particular materials. Then I have included different models. More importantly, here I have included models to look at the reverse breakdown characteristic of the Metal Semiconductor Metal photodetector. BBT stands for band-to-band tunneling, and impact SELB actually includes impact ionization via Silvaco model. I'm using Newton method for the numerical simulation of the semiconductor device. Here I want to look at various output characteristics of the structure, for example the energy band diagrams, electron and hole mobilities, etc. Then I save the structure with this name and plot the structure under thermal equilibrium. Then in this block, I actually want to look at the spectral response range of the photodetector. So here I'm introducing a beam of light with a wavelength of 0.1 micrometers, and at x is equal to 5 micrometers and y is equal to minus 1 micrometers, angled vertically upon the structure. And then I want to look at the spectral response range under biasing. So I'm sweeping the cathode voltage from 0 to 1 volts at a step of 0.1 volts. Then I'm running the wavelength sweep from 0.1 to 1.5 micrometers at a step of 0.05 micrometers. Here I have created a log file. We save the results inside the log file, and then using this command I'm actually plotting this log file which contains the spectral response range and information of the MSM photodetector. And then at this point I would like to look at the structure under light conditions. So I've saved the structure once again, and I'm going to plot the structure as well. After that, I want to look at the IV characteristics of the photodetector under dark conditions. So here is the code for that. I'm going to create a log file, and I'm running the voltage sweep from 0 to 16 volts, followed by looking at the IV characteristics of the MSM photodetector under light conditions. So here I have included another beam with a wavelength of 0.1 micrometers at this point, and then I initiate the illumination onto the device, where I am ramping up the illumination from 1 watt per meter square to 1 kilowatt per meter square to avoid any kind of convergence problems. And then here I'm looking at the IV characteristics of the MSM photodetector under light conditions, sweeping the voltage in the range of 0 to 16 volts. And finally, I'm plotting the dark IV characteristics and the light IV characteristics into the same figure using this overlay command. And finally, I quit the program. So now let us run the program. Here is my structure under thermal equilibrium. Let me display the contacts, and then I already showed you how to look at the doping levels. So we click on contours, and you can see the doping level. The doping level is 10 to the power of 17 per centimeter cube inside the semiconductor. Similarly, we can go to tools and then cut line and draw a cut line across the metal and semiconductor on the left side. And here we can display, instead of the absolute net doping, I want to look at the energy band diagram. So we can click on EC of T, then EV of T, and electron quasi-Fermi level. So here is the energy band diagram of the structure under thermal equilibrium. As you can see, there is a depletion region on the semiconductor side. Similarly, there is a Schottky barrier on the metal side, and there is a built-in potential barrier on the semiconductor side. This Schottky barrier on the metal side is approximately 0.725 electron volts. We can increase this barrier by using a material with a work function higher than 4.9 electron volts. Or you can reduce this barrier by using a material with a work function smaller than 4.9 electron volts. 4.9 electron volts is the work function value that we have used inside our structure. So we have looked at this metal semiconductor junction. We can also look at the energy band diagram across the right metal semiconductor junction. Over here. So basically we have got a Schottky barrier over here on the left side and another Schottky barrier over here on the right side. Here is the structure under illumination. So I can go to display and display the contacts. Similarly, I'm more interested in looking at the photo generation rate. So here is the photo generation rate. I hit apply and click on OK. Here is the photo generation rate across the structure. As we see, looking at the color chart, the photo generation rate is higher in regions which are exposed to light. However, the regions which are covered with the metal electrodes, the anode and cathode, under these electrodes, our photo generation rate is extremely low. So we can draw a cut line over here, like a horizontal cut line under the electrodes to see the photo generation rates. So as you can see, the photo generation rates are higher in the regions which are exposed to light. However, the regions which are under the metal electrodes have an extremely low photo generation rate. Similarly, we can draw a cut line over here to look at the energy band diagram once again. Let us disable the photo generation rate. So now here is the energy band diagram under reverse bias now. So if you compare it with the energy band diagram under thermal equilibrium, you might see that first of all, under thermal equilibrium we have a constant Fermi energy level. However, under reverse bias, the Fermi energy level is not constant anymore. Also, if you compare these two, we see that the built-in potential barrier on the semiconductor side has now increased under reverse bias. This is a simulation of another code that I was running at the same time. So let me close these figures. Okay. After this, I want to show you the spectral response range of this MSM photodetector. So we click on optical wavelength. We want to look at anode cathode current versus optical wavelength. Here is the spectral response range of the MSM photodetector, essentially running in the range of like 0.2 to 0.8 micrometers. And the peak value is observed at approximately 0.45 micrometers, or you can say 450 nanometers. Similarly, more importantly, I want to show you the IV characteristics of this structure under dark and light conditions. Okay, the red curve represents the IV characteristic of the photodetector under dark conditions, while the green curve represents the IV characteristics of the photodetector under light conditions. And if you zoom in on this region, you might see that the under light conditions we have approximately 3 orders of magnitude higher current as compared to under dark conditions. So we see the effect of light on this MSM photodetector. We saw the photodetection phenomenon. Now I want to show you the effect of lowering the metal work function on the IV characteristics. So I'm gonna close the remaining figures. And I'm gonna leave this figure as it is, and I'm going to make slight changes inside the code. Like for example, I'm going to reduce the metal work function now to 4.8 electron volts. Now this is going to reduce the Schottky barrier, and also we would see the effect of lowering this work function, or you can say reducing the Schottky barrier on the IV characteristics of the MSM photodetector. So let us run the simulation. Here is the structure under thermal equilibrium. Let us look at the energy band diagram of this structure under thermal equilibrium. Hit apply, and if we look at the Schottky barrier, now we see that the Schottky barrier has reduced to approximately 0.63 as compared to the previous one, which was 0.73. So the first effect is lowering the metal work function actually reduced the Schottky barrier. Now we want to see the effect of that on the IV characteristics under dark and light conditions as well. I'm going to close this figure. The simulation is still running at this point under light conditions. So we go to display, and we hit apply. Okay, so now here is the IV characteristics under dark and light conditions where I have reduced the metal work function. So if we zoom in on this region, now we see that the light current is approximately 1, or you can say 1 to 1.5 orders of magnitude, or you can say 1.5 orders of magnitude higher as compared to the dark current. Compared to the previous case where our light current was 3 orders of magnitude higher as compared to the dark current. So if you reduce the metal work function, reducing the Schottky barrier, we would see that it's going to reduce the on-off current ratio for the metal semiconductor metal photodetector. And you can make further changes, like you can further increase the metal work function, or you can even further decrease the metal work function to see the further variations in the output characteristics of this photodetector for using various kind of metals. So I posted this video on popular demand from some of my viewers and also from some of my students. I had it in my checklist for a while. Now that I found some spare time and the semester is over, I had the opportunity to create this video for you all. I hope it was informative for you. Until next time, take care. Adios.